Okay, today what I want to look at are reactions of monosaccharides, meaning single carbohydrates. And the reactions I want to look at are pretty straightforward. The first one is acylation. And if you think about what the word acyl means, right? An acyl group is a specific functional group in organic chemistry. Specifically, it's a methyl ketone, right? So when you look at an acyl group, what you're really looking at is this, and it's oftentimes shorthanded in biochemistry and organic chemistry as just AC. Just like we would see a pH for phenyl, AC is code for this acyl group. So you can do acylation of carbohydrates pretty readily. And so let's go ahead and see what happens if we try to acylate glucose. And in this case, I'm going to look at beta D-glucose, but this will work on alpha D-glucose as well. It doesn't really matter. And so here we've got D-glucose. And if we want to acylate it, we need a good acylating reagent. And this is something we actually talked about during our carboxylic acid derivatives chapter, that if you want to install that acyl group, you must have some sort of good leaving group in that position. That allows for nucleophilic acyl substitution to occur. So a good reagent for this would be acetic anhydride. Now, I know a lot of you might be saying, well, why not the acid chloride? Well, in this case, the acid chloride, it could work. It's just really, really reactive. So in this case, we'll use the reagent that's most gentle for this situation. It's going to be easier to control. And in this case, this whole side over here is going to act as our leaving group. And then this whole side is essentially going to be our acyl group. And when you do this reaction, you typically do it in excess. But as you can imagine, each one of these alcohols can act as a nucleophile, attack into acetic anhydride, and acylate each one of those alcohols. So let's go ahead and draw our acylated product. If we do this, let me clean this up a bit more. Each one of these is going to essentially become a little ester. So if you think about those AC groups, they're methyl ketones, but when we tag an oxygen to the other side, they all of a sudden are esters. So we could react with any one of those alcohols, just like we saw in that carboxylic acid derivatives chapter, to make an ester. All right, the next one we're going to look at is kind of similar. This is called alkylation. So as you can tell, we're going to install alkyl groups. So similar sort of chemistry. We're going to look at D-glucose first. Sorry, my handwriting's not the greatest today. Too much coffee. So we've got D-glucose over here. With all of the substituents coming off. And if we want to alkylate it, we need some sort of alkyl group that has a good leaving group attached. So the most common one that we might see would be something like methyl iodide, right? Because the methyl group acts as the alkyl group, iodide acts as our leaving group, and we can do a substitution reaction with every single one of those alcohols, because each of the alcohols on glucose can act as a nucleophile and do SN2 chemistry. Oftentimes what you'll see is when this reaction's done, they use silver 1 oxide. And the reason that they use silver 1 oxide is that this will precipitate out as silver iodide solid. So the nice thing with this is you can remove, oh, that looks like it's misspelled. It precipitates out as silver iodide solid, and that helps get rid of any of the iodide from the solution and makes the reaction much cleaner to carry out. So when we do this, we're going to react every single one of these nucleophilic alcohols with methyl iodide and do an SN2 reaction. So let's take a look at what we get out from this reaction. We're not going to get an ester. Instead, what we're going to do is create a bunch of little ethers. But as you can see, it's not very selective. It's going to react with all of these. So typically, you just do this in excess in order to push the reaction to completion. All right, these aren't the most useful reactions because they're not very selective. If you go on into higher level chemistry, you can figure out unique protecting group schemes to block certain alcohols and only react the remaining ones. But that gets into really high level chemistry that we're not going to cover in this course. All right, so let's take a look at more interesting chemistry. These are kind of generic. The next one I want to look at is called glycoside formation. And this one's a lot more common because it's more selective, meaning it's not going to react with all of the alcohols, it's only going to react with one of them. So let's go ahead and see how this works. All right, so again, I'm just going to use beta D-glucose as my starting material. And the first step in glycoside formation is to react it with an alcohol. In this case, I'm going to call my alcohol just a generic HOR. And I'm actually going to change the color to green just so you can keep track of all of those atoms. And in addition, you need catalytic acid. And the first step of this reaction is to protonate your anomeric alcohol. So if you think about this, this is the anomeric position, which means that this must be my anomeric alcohol. And we're going to protonate right there. Now, some students will ask, why that one and not the other one? Well, the truth is the other ones will get protonated, but it doesn't take you in any sort of useful direction. This alcohol, when you protonate it, takes you somewhere useful, meaning the reaction can proceed further and it's not just a dead end. So let's take a look. If we protonate that alcohol, we're going to obviously turn it into a good leaving group. So this is a good leaving group. But the nice thing with this is if that leaving group falls off, as opposed to any of the other alcohols, whoops, that shouldn't have a 2, it forms a resonance stabilized carbocation. And so what I mean by that is let's kick off this alcohol. If I do that, I've got a positive charge, which is what would happen if any of these alcohols fell off as water. However, the nice thing with this is we can resonance stabilize it and delocalize that positive charge to the neighboring oxygen. So that's why that alcohol is always shown. It's not that the other ones don't react, it's that this one leads to a stable carbocation intermediate. So we've got both of these resonance structures, and in this case, the one on the left is actually the major contributor because it has complete octets on every atom. Now, the other thing we've kind of neglected is we still have this alcohol floating around in solution, right? So if this alcohol is still floating around in solution, this alcohol can react with this carbocation. So we can have it attack right there and kick up electrons to oxygen, and we still have water kind of floating around. So as you can imagine, if you want to do this reaction, it is reversible, meaning the water that was kicked off could attack right back in and push you back to your starting material. So one way to favor formation of the glycoside product is to use an excess amount of alcohol. That way you outcompete the water and get it to attack in more readily. All right, so when we do this, we're going to get a new carbon-oxygen bond formed. However, now it's going to look kind of something like this. Now the weird thing with this, right, is I've shown this as the beta form. However, it could attack either way. So let's go ahead and just copy this over and we'll draw both of them. So I'm going to copy and paste this over here. And we could have the axial form. So if you remember, these are called anomers. They're diastereomers that differ only at this anomeric position, and that's because if we think about the carbon that we added into right here, it's trigonal planar. We don't have a strong preference really for attacking the top or bottom face. We don't get a perfect 50-50 mixture, but we do get a mixture. And then as you can imagine, in the last step, we're just going to deprotonate. So I'm going to write -H plus. And then with the power of my tablet, I'm just going to copy all of this down, and we're going to remove that extra proton and get to our final neutral product. So let's go ahead and paste that and show this. All right, so deprotonation gives you your final neutral product, and this would be called a glycoside. We need to get rid of these positive charges, and this would be our final product. The interesting thing with this is these are called glycosides. Specifically, these are called O-glycosides. If you think about it, the O kind of makes sense. This stands for an oxygen-based glycoside, meaning some sort of oxygen nucleophile added in this case an alcohol. This can occur if you use nitrogen-based nucleophiles as well. And as you can imagine, if it's a nitrogen nucleophile, you're going to get an N-glycoside. So amines give N-glycosides. All right, so this is pretty common chemistry. It's nice because you're only reacting one position. You're not touching any of the other alcohols. So it's kind of useful. All right, the next thing I want to do is look at oxidation chemistry. The oxidation chemistry is kind of fun. And again, it tends to be more selective. So this time I'm going to switch and draw the Fischer projection form. So again, I'm going to stick with D-glucose, but we're going to show the open chain form because it makes more sense to think about oxidation occurring at the open chain form. And specifically, we've got an aldose here, right? Because it's got an aldehyde on the top. And as you can imagine, we can oxidize this. And specifically, we can oxidize this using two different methods. The first method I want to use is our more gentle oxidizing agent. And this is done with bromine and water at a pH of 6. And I'm just going to make a note here that this is gentle. So if we think about what's going to be oxidized, we could imagine oxidizing a number of different positions, including the alcohols. However, the aldehyde's actually the first thing that's going to get oxidized during this reaction. So if we go ahead and we oxidize it, the next oxidation state it can go to is a carboxylic acid. So really what we're doing is we're converting this aldehyde to a carboxylic acid, but everything else is going to remain untouched because the oxidizing agent isn't strong enough. Let me fill in the rest of these, and we've got our product. This is referred to as an aldonic acid. It just means that it's a aldose that's been oxidized all the way up to its carboxylic acid state, but that's it. All right. Some students will ask, well, what happens if you use stronger oxidizing agents? Well, you can actually do this. And so let's take a look at the next strongest conditions. You can use HNO3, it's nitric acid, water, and heat. If you do this, you're actually going to oxidize not only the aldehyde, but now the next most reactive site. And the next most reactive site is going to be the primary alcohols. It's easier to oxidize a primary alcohol than it is any of the secondary alcohols. So when you do this, you're going to oxidize the aldehyde, but also oxidize that bottom primary alcohol all the way to a carboxylic acid. So now we've oxidized this top position and that bottom position. All right, so let's take a look at what this is called. This is called an aldaric acid. This isn't commonly done. In fact, it was done primarily in the early 1900s when they were trying to deduce the structures of these carboxylic acids. And by doing this, it's kind of neat. We've created mirror images of carboxylic acids. And so they basically did tests of optical rotation. And as you can imagine, if there was optical rotation, that could be used to tell you, hey, these aren't symmetric. If there wasn't optical rotation, you could tell, hey, there's symmetry going on in those OH groups, and they use that as kind of this long test to figure out, hey, what's the structure of this carbohydrate versus another carbohydrate. If you're interested about that, in reading more about that, Emil Fischer was the chemist that did a lot of the pioneering work behind finding the structure of these carboxylic acids. All right. After this, students will typically ask, hey, you're not using the standard oxidizing conditions we normally use. What about chromic acid? What happens if you use chromic acid? The reality is, if you use chromic acid, it's kind of like throwing a hand grenade into your reaction flask. It'll oxidize everything, and it will run away. In fact, I've got a cool video to show you. Okay, so in this video, this person has cane sugar, which consists of carbohydrates, right? And what this person's going to do is combine this with sulfuric acid, concentrated sulfuric acid, mind you, which is a really strong oxidizer. And I want you to see what happens. It's going to oxidize every single one of the available alcohols. And when that happens, it produces a fair amount of heat. So I've got this set up with the time lapse. It'll speed up his reaction a little bit. But you can see he's adding about a cup or so of sugar. Going to grab his sulfuric acid. Luckily, he's wearing gloves. This is something I would not do at home, but it's okay to watch it on YouTube. And he's going to mix it up with his stir rod. And you can already see a color change occurring. Some of you may have noticed that when you wipe sulfuric acid with paper towels, it turns black. Same reaction. Right? You're oxidizing the carbohydrates in the paper towel, turning it black. And he's going to keep on stirring it, and it's getting pretty warm. So he's using tongs to move it around. It's now too hot to move with his hands. And it's getting warmer and warmer and warmer, and to the point where it will actually start cooking itself. So when students ask, why don't we use chromic acid with these carbohydrates? Well, we don't want to cook our product into this thing that looks like a snake of carbon. Okay, so looking at these reactions, it's interesting. We can oxidize the aldehyde or the primary alcohol using the appropriate reagents. However, if you go way back to general chemistry, you'll remember that because this is getting oxidized, it's acting as a reducing agent, right? Where these, on the other hand, are acting as the oxidizing agent. All right. And because the aldehyde's acting as a reducing agent, this sugar is called a reducing sugar, meaning it's a sugar that can be oxidized. All right, now a lot of times what students will see is reducing sugars, but in the context of the closed ring form. So let's go ahead and draw this out really quick. And what I want to do is compare a reducing to a non-reducing sugar. So let's draw them out. So reducing versus non-reducing sugars. Oops. And so what I'll do is over on the left, I'll draw a reducing sugar. And we said that glucose is a reducing sugar. So the example I gave above, we could oxidize either the aldehyde or the aldehyde and that primary alcohol. All right, so here's our closed ring form of D-glucose. And like I said, the most susceptible sites are going to be that anomeric carbon. If you think about it, that's the carbon that can ring open, form an aldehyde, and be oxidized to a carboxylic acid, or this alcohol. So both of those sites are susceptible to oxidation. All right, let's look at non-reducing sugars. And these look really similar at first glance, but there's a subtle difference. So let's go ahead and draw this out. Oops, sorry, this should be OH is here. Sorry about that. The main difference between a reducing and a non-reducing sugar is this position. You see how this is an O-glycoside? Because it's an O-glycoside, it's not going to react with those traditional reagents like bromine and water. The main thing to remember is that reducing sugars have an OH coming off the anomeric carbon. And because of that, it can more readily ring open, form an aldehyde, and get oxidized. That's the key feature here. Now the cool thing with this is that there's a test for this, and we can take a look at this video here in a second. But before we do this video, I quickly wanted to show you what they're doing. This is called the Tollens test. And the Tollens test was done for many, many years as just a qualitative test to see if you had a reducing sugar. So in this case, this is going to be our reducing agent, our aldehyde on our ring open formed of our sugar. And what they're going to do is react this with silver cations. And the silver, in this case, is going to act as the oxidizing agent. And we're going to get some electron transfer chemistry to occur, meaning redox chemistry. And we're going to oxidize our aldehyde to our carboxylic acid. But if you think about it, the oxidizing agent's going to gain electrons during the process. So if silver gains electrons, it's going to form silver metal. So if we think about it, what's happening here is we're forming shiny silver. And if you've ever seen silver, it has that metallic luster to it. So chemists could quickly say, hey, I'm seeing solid silver forming. It must mean that I was working with a reducing agent. All right, so let's take a look at this video.
If you'd like to stand there, just pop those on. What's your name?
Dylan.
Dylan. All right, Dylan, if you stand just there, we're going to do some chemistry and we're going to make it a solid. All right, I'm going to start off with a flask that contains a solution of silver nitrate, and I'm going to add a little bit of ammonia. Now when I add the ammonia, you see that it's forming a sort of brown colour. I'm going to keep on adding the ammonia, and in a minute that brown colour should disappear. Oh, it's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So I'm now going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. This takes a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. Now I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan, and I want you to hold that. And I want you to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. This takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works. So keep shaking. Don't drop it, though. Okay. So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the of the flask. And as they build up, we should see silver metal in the form of a mirror building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. The little balls of glass and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, let's have a quick look. Almost there. Keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to me then. Right, so I'm going to take the clip off. Take out the stopper. Just wash that off. And I'm going to pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. I'm going to rinse it out a second time. Rinse it out a third time. There we go. And just going to put that on, just dry this off. And put the clip back on. And if you'd like to just give that a little polish. There we go. If you like to hold it up by the neck, that's it. And if we bring a camera in and have a look at this, and we've got a lovely silver mirror.
So the tolerance test was used for many, many years. It's one of my favorite live demonstrations, which is why I wanted to show you the video. In fact, that's how mirrors were made for a long time. Obviously, it's pretty expensive to use silver, so it's not commonly used anymore. All right, so the next couple of reactions I want to do are reduction and then epimerization. I apologize that this video is a little long, but I just wanted to try to encapsulate all of the important reactions into one video. So for reduction, this one's luckily a lot more intuitive. So let's go ahead and draw out D-glucose. And D-glucose looks like this, where we've got all of these different groups coming off. Again, I don't expect you to memorize the structure of all of these, but we can imagine reducing this aldehyde rather than oxidizing it. And if we reduce it, what will it become? Well, it would become a primary alcohol. So again, you would get the CH2 group down here. But now we'd get a new CH2OH group on the top. And when we form this molecule, we refer to this as an alditol. It's essentially a fully reduced carbohydrate. The easiest reagent we have to reduce aldehydes is sodium borohydride. So luckily, we don't need to remember anything new for this reaction. It's just the standard conditions you would use to reduce any aldehyde, which is pretty nice. All right, the last reaction I wanted to look at is epimerization. And if you remember back to the previous video, an epimer is a set of epimers are a set of diastereomers that differ at only one stereocenter. But it's not the anomeric carbon, it's one of the other carbons. So let's take a look at how this happens. So if we have an aldehyde, like D-glucose, this can happen in the presence of base. So let's go ahead and draw out all of these. And if you have a base like hydroxide, it's going to be searching for the most acidic proton, or another way of thinking about this is it's going to be looking for the site where you can deprotonate that will give you the most stable conjugate base. In this case, it's not the proton that you might expect. In this case, it's going to be this alpha proton right here. And in this case, what we're going to do is we're going to pluck off this alpha proton, kind of like what we saw in the previous chapter, and kick up electrons to that oxygen. And when we do that, we're going to basically create an enolate, right? So we'd have a negative charge here, double bond there. We'd have an OH sticking out there. We'd still have this crossbar going down. The bottom half is basically remaining untouched during this entire process. So we can go ahead and we can fill that in. and we've made our enolate from our aldehyde. But we still have water floating around, and when this happens, we can deprotonate the water and we can make our enol. So let's go ahead and draw out our enol. So I'll do the bottom half and then we'll build up. Now we've got a double bond right there. We've got an OH here and an OH there. And so we've gone from our enolate to our enol. So a lot of this should look pretty familiar to you. All right, the interesting thing though is we can do other chemistry. So if we think about this going the reverse direction, this can also grab a proton from water through this mechanism, where instead of forming the enol right away, some of this enolate could react. Sorry, that's not the best arrow. And deprotonate water and go straight back to our aldehyde. And if that happens, we could get a mixture of two different products, because we've kind of lost stereochemistry at that top position, right? So we could just go right back to our starting material, which is D-glucose. However, that top stereocenter, meaning this one right here, could be scrambled, meaning we could get a mixture of two different molecules. So we could get one where maybe the OH on the top is now off the left rather than the right. And so what we've done is we've gone from D-glucose, that was our original molecule, back to some D-glucose in this equilibrium that's constantly kind of bouncing back and forth. But we're also creating a new molecule over here that is an epimer of D-glucose. I can't remember the exact name of this carbohydrate off the top of my head, but as you can see, this top stereocenter is now flipped, right? So because we flipped one stereocenter, these would be referred to as a set of epimers. All right, so we're going to stop there. When we come back tomorrow, we're going to look at chain lengthening and chain shortening.